Aluminum is light. Aluminum is shiny. Aluminum is great until you ask it to do literally anything stressful. Then it folds faster than a lawn chair at a barbecue. But somewhere along the way, scientists figured out how to take this soft, easily bullied metal and turn it into something shockingly tough without making it heavy, ugly, or emotionally distant. And the secret isn't brute force. It's copper, heat, patience, and a little bit of scientific chaos. I'm Professor Everything, and today we'll be answering the question, how is Duralumin made? Right here on Explaining Everything. Pure aluminum is a people pleaser. It's lightweight, corrosion-resistant, and incredibly easy to shape. Unfortunately, it's also not very strong. Apply pressure, and aluminum doesn't resist. It negotiates. Poorly. Early engineers loved aluminum's weight, but hated its lack of backbone. So they asked a dangerous question. What if we messed with it? That's where alloying comes in. Alloying means mixing aluminum with other elements to change how its internal structure behaves. For Duralumin, the star guest is copper, with magnesium and manganese playing important but quieter supporting roles. When copper atoms slip into aluminum's crystal lattice, they don't fit perfectly. This creates internal stress, which makes it harder for the metal's atomic layers to slide past each other. Translation: the metal gets stronger because its atoms are slightly annoyed at all times. But just tossing copper into aluminum doesn't magically create Duralumin. That's like buying ingredients and calling yourself a chef. The real transformation happens later. Making Duralumin starts in a furnace. Aluminum is melted first because it makes up most of the alloy. Once it's fully molten, copper is added, usually around 4%, along with small, carefully controlled amounts of magnesium and manganese. And yes, the measurements matter. This is metallurgy, not cooking pasta. Too much copper and the metal becomes brittle. Too little and it doesn't strengthen enough. There is exactly one sweet spot, and missing it ruins everyone's day. Once everything is fully mixed, the molten alloy is poured into molds and allowed to cool into solid form. At this stage, it looks finished. It's shiny. It's solid. It feels strong. It is lying to you. Because right now, this alloy is only potentially Duralumin. The atoms are in the right ratio, but they haven't been properly trained yet. For that, we need heat. Again, but very carefully. The solid alloy is reheated to a high temperature in a process called solution heat treatment. This forces the copper atoms to fully dissolve into the aluminum structure, creating a uniform atomic mix. Then comes the most dramatic step, quenching. The hot metal is rapidly cooled, usually by plunging it into water. This sudden cooling traps the copper atoms in positions they don't want to be in. They're stuck, uncomfortable, and very eager to rearrange themselves. Here's the weird part. Right after quenching, the metal is actually softer than expected, which feels like a scam. But stay with me. After quenching, the alloy is left alone to age. During this time, copper atoms slowly group together into tiny clusters inside the aluminum. These microscopic particles block movement within the metal structure, preventing internal slipping. That resistance is strength. This process, called precipitation hardening, can happen naturally over time or be accelerated with gentle reheating. Either way, the metal literally strengthens by sitting still and letting physics do its thing, which is deeply unfair but impressive. Here's the best part. This entire process was discovered by accident. In the early 1900s, German metallurgist Alfred Wilm noticed that an aluminum-copper alloy he had quenched seemed stronger a few days later than it was immediately after cooling. Most people would have blamed bad measurements. Wilm paid attention. He realized the metal was changing over time without any extra work. That observation led to the understanding of precipitation hardening, the defining feature of duralumin. Once scientists understood what was happening, duralumin production became a game of precision. Exact temperatures, exact timing, exact compositions. Miss a step and the alloy doesn't behave the same way. Get it right, and the metal becomes significantly stronger without gaining much weight. No mystery, no magic, just atoms doing slow, petty rearrangements. To recap, it starts as aluminum with ambition. Copper gives it potential. Heat shakes everything into place. Rapid cooling locks in tension. And time, glorious, boring time, finishes the job. Duralumin isn't strong because it's forced to be. It's strong because it's carefully prepared and then allowed to become what physics intended. Which honestly might be the healthiest character arc any metal has ever had. If you enjoyed this deep dive into metal that literally gets stronger by waiting, don't forget to like and subscribe. Also, if you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. If you enjoyed this video, please check out our other bingeable channels. Thank you for tuning in, and join us next time here in the channel that answers all the why, what, who, where, and how questions you've always wondered about, here on Explaining Everything.